Hello, everyone. My name is Ranran Chen, and I'm from the University of Texas at San Antonio. Today, my topic is about detection of multiple undocumented change points using Bayesian adaptive lasso with quantile regression models. So let's first talk about some background information about change point detection. So change point detection task is concerned with identifying the position where the behavior of the series changes dramatically. For example, relocation of weather station or change of observing instrument will lead to abrupt shifts in temperature records. And financial crisis or economic stimulus will lead to significant change in stock market index. So we're trying to find the positions where these changes take place. So Bayesian and others used a frequentist linear model, which includes a dummy variable for each potential change point, and then employed adaptive lasso and multivariate simultaneous confidence intervals to select significant change points. To be more specific, they estimate beta j, the amplitude of the mean shifts from the last time step to the current time step by the following adaptive lasso objective function, which is here. So the M here is the centralization term, lambda n is regularization term in adaptive lasso, and Wj is a pre-selected weight vector. And in this project, contrasts to the frequentist approach, we've developed a fully Bayesian adaptive lasso approach using quantile regression models. And compared to traditional frequentist linear square regression, a fully Bayesian quantile regression is more robust against outliers, and it is able to deal with a large class of error distributions. The objective function of the quantile regression model is defined as follows. And beta is as defined in equation 1, which is here, the amplitude of the mean shift from the last time step to the current step. And tau is the quantile level. So minimizing equation 2, which is the objective function here, is equivalent to maximizing the likelihood function of yi by assuming yi's are random variables from a skewed Laplace distribution. And it has density function here. And we notice that skewed Laplace distribution can be represented as a skewed mixture of normal distributions, which has a form here. And the Vt here follows an exponential distribution, and the Et follows a standard normal distribution. So why do we use mixture representation? Using the scale mixture representation of normal distributions as an alternative prior for Yt help us to express a quantile regression model as a normal regression model. And it helps us to construct the Gibbs sampler easier for all other parameters in the model. So the Bayesian adaptive lasso quantile regression is a Bayesian hierarchical model given as follows. These are the prior distribution for all the parameters. And then by the above discussion, we can sample from the joint distribution by Gibbs sampling as follows. So these are the posterior distribution. And we notice that all these posterior distributions are common distributions. So we can sample directly from these common distributions. So it can save us a lot of time, and it will higher the calculation efficiency. So let's talk about the simulation part. In the simulation setting, we simulate random sequences from the true models. And the epsilon follows a normal distribution or a t-distribution. And 6 change points are positioned at 20%, 40%, 50%, 70%, 75%, and 85% of the sequence. And the jump size of each change point is 3, which has this form. So we basically use the edge to add some abrupt mean shift to the data series. And the job is to find the position of the abrupt shift, which is the change point. We simulate 200 sequences when n equals to 100 and 200. So after simulation, when n equals to 100, we plot histograms of positions that is detected by both Bayesian and adaptive lasso approach. We conclude that both approach can identify the position of change points in the simulation data with high probability. But Bayesian approach seems to be a little more stable and comes with lower false alarm rate. And when n equals 200, the plot indicates that both approaches can also find correct locations of change points with high probability. Therefore, we conclude that under our setting, both approaches are comparable. We have also done simulation for epsilon follows normal and epsilon follows t distribution. In both settings, Bayesian approach can significantly reduce false alarm rate. And especially when epsilon follows t distribution, the false alarm rate from Bayesian approach is only around 1/3 of the false alarm rate from frequentist approach, which confirms the claim that fully Bayesian approach performs better dealing with a large class of error distributions other than normal distribution. So let's apply our model to a real data problem. Here we consider weekly log returns of Dow Jones industry average. The time period under consideration is April 1990 to January 2012, which comes with 1,139 observations. So from the result table, it shows that the change point days detected by both Bayesian and frequentist adaptive lasso approach, which is here. The result confirms our conclusion from the simulation part. Frequentist approach has higher false alarm rates. And this table shows the events, which is here, and corresponding dates, which is here, which are considered as the true change point positions. And the correctly detected dates are around true event dates from the Bayesian approach, which is here. We conclude that over 80% of detected change points from the Bayesian approach are correct. So in this project, we developed a fully Bayesian adaptive lasso approach to estimate the number and locations of change points. The proposed method extends the Bayesian adaptive lasso that consider quantile regression to improve robustness against outliers and a large class of error distributions. Both the simulation results and real data application shows that our fully Bayesian approach could outperform frequentist linear model approach in terms of both detection rate and false alarm rates. And here are the reference. All right. Thank you everyone for listening.